Hi, this is Mrs. Roble. This is part 3 of the structure of the atom. So we've talked about the classical structure of the atom, and then we've discussed the modern structure of the atom. Now we want to focus in on the nucleus, and with the nucleus comes what we call nuclear changes. And you're probably more familiar with radioactivity, and that typically happens during nuclear changes. Before we start talking about radioactivity, I wanted to discuss some of the natural sources of radiation that you are exposed to. Right now I'm sitting outside, it's a beautiful sunny day, and I'm actually being exposed to cosmic background radiation. The good news is most of our atmosphere actually protects us from a large chunk of the cosmic background radiation, but that is the largest exposure that I typically get in a year, and the same with you. You could have dental x-rays, or maybe you broke a bone. That's still only a fraction of the total exposure that you get naturally. In your home, you actually have a source of radioactivity. This is a smoke detector, and it contains a source of americesium. And americesium looks at the ionization changes. So when smoke flows through in the detector, it sets off the alarm because it notices the rate of ionization has changed. It used to be that these mantles that were for propane or white gas lanterns, they used to put thorium in them. Now, they don't have thorium anymore, but if you have one of these old ones lying around, it probably contains a little bit of radioactive thorium. Thorium is good at emitting light in the visible range, and that was the reason why they put thorium on these mantles, but thankfully now they just put metal oxides. So looking at nuclear changes, there's actually 3 types, and this one you may be familiar with, gamma ray emission. So notice that gamma ray emission is high energy. If you want to stop gamma ray, because it's high energy, you typically have to have concrete or lead. So when you go to the dentist office and they're about to take dental x-rays, notice they put the lead apron over you. And the reason why is they're trying to stop the gamma emission. The interesting thing is, how come they're not putting anything over your eyes? I'm curious about that. I guess patients don't care about gamma affecting their eyes. And notice that gamma has this interesting Greek symbol. Don't be surprised to see that in some of our calculations. All right, the next type is actually from smoke detectors and a lot of radioactive sources. Alpha. Alpha is actually similar to a helium mass number 4 nucleus. It has this Greek symbol. The nice thing about alpha is it actually can be stopped by your skin or clothing or even a piece of paper. So alpha is not as penetrating, it's not as deadly, I guess you could say. So here's an example of alpha decay. So we have a plutonium nucleus on the left. Notice we lose a alpha particle at the bottom, and plutonium is transformed into another nucleus, which is uranium. And notice you go from a mass number of 240, so the number on the top is the mass number, to 236. So we lost 4 mass number units, and then we have an atomic number of 94 down to 92. So please remember, the atomic number determines the type of element. So it actually transforms from plutonium to uranium. Okay, the third type is beta emission. Beta emission is not as nice as alpha emission. Beta emission, you actually need to have thicker clothing, you need to have a thicker piece of metal to stop beta emission. So beta emissions will penetrate your skin, just to let you know. the beta particle is actually negatively charged, and we typically associate it with an electron. Another term for it would be negatron, and notice that it has this Greek designation. So here we have a mass number cesium-137 that it doesn't change, okay? So try to remember with beta emission we have no change in the mass number. However, and this is the bizarre thing, the atomic number actually increases. So beta emission we go from 55 atomic number to 56. So we transmute from cesium to barium. Okay, so because of the conservation of mass, we have to have good accounting of where that mass is going. So notice that if you have alpha emission, we have an alpha particle. Beta emission, we have a negatron or a negatively charged electron. And the gamma actually is not a particle, just to let you know. Okay, it's just pure energy. So alpha has mass of 4, beta is 1/1840th of an AMU, sorry. And then gamma is massless. So gamma has no mass. Notice that the charge for alpha is a 2 plus, beta is 1 minus, and then gamma is 0. Okay, here is a transmutation of uranium. Notice that uranium starts off as U-238 and through a series of transmutations. So it actually goes through all these different elements and it ends up as lead. Okay, so lead is the least benign substance because it's depleted. So uranium eventually loses all of its radioactivity, its nucleus stops changing, and then it finally transmutes into lead. Don't be surprised if we do a chart like this in class. We'll practice that. Okay, here are some non-spontaneous changes. So nuclear fission, this is not something that happens naturally. You need to have some kind of impetus, some kind of change. And if you notice on the bottom here, we have a neutron that comes in contact with a large nucleus. And this large nucleus, it loses its attraction with itself, and it eventually splits into more than one nucleus. And notice that we have emission of particles. The first atomic bomb was made up of uranium mass number 235. 235 is not a high concentration naturally. They had to enrich the material, so they were essentially able to distill out just mass number 235 in a large concentration. It was a very laborious process. You know, it takes a lot of time. The second atomic bomb was plutonium 238. And typically nuclear reactors, so if you go up to Perry by the lake, or there's another reactor near Vermilion, the Davis-Besse plant, both of those plants use uranium rods of 235. This is just some background. The first atomic bomb that was unleashed over Hiroshima, notice that it weighed approximately 8,900 pounds. It essentially was equated to 13 to 16 kilotons of dynamite. However, the scary thing is the average atomic bomb made nowadays, we're talking about 500 megatons. So an extremely powerful nuclear weapon that obviously countries need to work at not deploying. Now, in order for a nuclear bomb to work, there has to be an explosive device that is attached to the unit. Notice that you have a uranium bullet, and it's essentially being fired by the explosion. And as it comes in contact, it creates the fission, which eventually creates the explosion. So in the bomb that they had, we're talking about 64 kilograms of uranium. Only 0.7 underwent fission, and an even tinier amount became energy. But that energy is just so exponential when you think about it. On the other side of radioactivity, we need to discuss half-life. Notice that half-life is the time that it takes for half of the sample to decay. So try not to confuse things too much. Now, that doesn't mean that the sample disappears by half. It just means that half of that sample has transmutated into something else. Please note that every sample, every element has a different half-life. When we're looking at archaeological digs, find carbon dating to be very useful, and the reason why is the material typically is organic. That means it's made of carbon. It had to be alive at one time. A piece of metal or something that is not organic won't work for this type of dating. Notice that for carbon dating we're talking about over 5,000 years. So it takes over 5,000 years for half of the sample to transmutate into another element. Okay, this is a very useful chart. Notice that the radioactive decay of bismuth at 100%, it takes about 5 days for half of the bismuth to transmutate into something else, and then 10 days, and so on. The faster the transmutation or radioactive decay, the more dangerous it is. So please remember that. With this equation, 1 over 2 to the nth power, so if we waited for 3 half-lives, we would essentially have 1/2 to the 3rd power, which is essentially 1 over 8. So we have 1/8 of the original material left. Here is an example of an animal that underwent radioactive decay, and notice that only a small portion of it is actually C14. So a good chunk of the organic material is carbon-12, which is not radioactive. So when scientists are measuring radioactive isotopes, they're measuring a very small amount. So notice with the first half-life, we have to wait 5,730 years for half of carbon-14 to transmute into nitrogen-14. And then if we wait another half-life, we have 1/4 left. And then lastly, we have 1/8 left after 3 half-lives. Please remember that half-life depends on the type of atom. Like I said, the quicker the half-life, the more dangerous the radioactivity. It doesn't matter how many atoms there are. It just means that a certain fraction of those atoms will transmute into another element. No matter how many atoms you have, half of them will decay. So if I have 32 atoms, 16 of them are going to decay into nitrogen.